Previously, we characterized properties of basis vectors and found that in an n-dimensional vector space, we need n basis vectors. That is, n vectors that are linearly independent. In the previous two videos, we used the inner product to compute the length of the vectors and the angles between the vectors. In this video, we're going to discuss the special case where the basis vectors are orthogonal to each other and where the length of each basis vector is 1. We call this special case an orthonormal basis. More formally, if we let B1 through Bn be a basis for a vector space V, and if the inner product of Bi and Bj is 0 when I is different from j, but 1 if I is equal to j, then we call the basis an orthonormal basis. In this definition, we point out that the second condition indicates that the basis vectors have unit length. Let's recall that we can use Gauss elimination to find a basis for a vector space spanned by a set of vectors. Let's assume that we're given a set B1 tilde through Bn tilde of non-orthogonal and unnormalized basis vectors. We can concatenate them into a matrix capital B tilde consisting of each of the B vectors as columns of the matrix. We can then apply Gaussian elimination to the augmented matrix B tilde transpose B tilde, and what we get is an orthonormal basis in terms of the rows of the new B tilde. This is a constructive way to iteratively build an orthonormal basis. We generally refer to this as the Gram-Schmidt process. Here's an example of two bases in R2. Our standard basis, 1, 0, and 0, 1. We can see that B1 transpose B2 is 0, and that B1 transpose B1 is the same as B2 transpose B2, and those are both equal 1, because they're unit length. Our second basis, 1 over root 2, 1 over root 2, and 1 over root 2 negative 1 over root 2, again satisfy B1 transpose B2 equals 0, and also satisfies norm of B1 equals 1, and norm of B2 equals 1. This is an important idea to understand because we're going to exploit the concept of this idea of orthonormal bases when we discuss support vector machines and principal component analysis. Going back to the idea of coming up with an orthonormal basis, let's consider the vectors 0, 1, 0, 1, negative 2, 3, 0, 1, and 1, 1, 1, 5. If we calculate A transpose A, we get the matrix 2, 4, 6, 4, 14, 6, 6, 6, 28. Now, if we put this into an augmented matrix, augmented with A transpose, and apply Gaussian elimination, we get on the left 2, 4, 6, 0, 6, negative 6, 0, 0, 4, and on the right 0, 1, 0, 1, negative 2, 1, 0, negative 1, negative 1, negative 1, 1, 1, and the rows of the right side are linearly independent. The square of their length value is the main diagonal of the left side of the matrix. So in fact, dividing by the square root of the entry on the main diagonal of the left matrix the rows of the right matrix are actually an orthonormal basis for the span of the vectors we started with. In the next video, we're going to get into the idea of an orthogonal complement and see how that will help us more easily come up with orthonormal bases.